Okay, so we're going to have a look at another few of the questions from the Born-Haber cycles and lattice enthalpy calculations for the AT chemistry. So I did a video previously on this here, and you'll see that the questions, we are currently on page 11 of the questions. So you'll see before that in the last video I've done the questions down to page 10. So I'm going to pick up from here. We'll do another few of these, and hopefully by the end of me doing all of these, you'll have a pretty good idea and be able to tackle the past paper questions that come your way, right? So we'll take our way through these. Okay, so first question is then we've got to write some simple equations, including state symbols. These are always important whenever we're doing our Born-Haber cycles, because a lot of them are definition driven, and obviously the definitions include state symbols. So you always must make sure and put those in, right? So the first state symbol for the first ionization energy of calcium, very simply, we've got calcium, which as we know is a solid, but remember for ionization energy, we've got to start it off as a gas. If you start off calcium as a solid, you're going to lose marks, okay? First ionization energy is the loss of 1 electron, okay, to make 1 mole of unipositive or +1 ions. The second ionization energy of that is we start with the calcium as a +1, okay, and we go Ca2 plus this time. It's a gas, and again we've lost another electron. We do not, I put the 2 in there, but we do not put the 2 in there, okay, because we're only losing 1 electron from this step to this step. So please make sure that you don't put the 2 in. All right, okay, and we're on to electron affinities, and we're looking for an equation to represent the first electron affinity of bromine. Okay, so bromine is a gas. Okay, in electron affinity, it's gaining an electron, and we're going to bromine, still a gas, of course, and that's -1. So remember, we're not starting here with, common mistake would be people writing Br2, half Br2 gas. It will already have been atomized by the time you get to the first electron affinity. The enthalpy for the atomization of bromine, so remember enthalpy of atomization is not like bond enthalpy. So the enthalpy of atomization is the enthalpy change whenever you make 1 mole of gaseous atoms. Okay, so therefore we got to start with half. It's got to be gas here, okay, and we're going to our actually bromine will be a liquid, won't it? Okay, we're going to bromine as that. So the bond enthalpy, if I was asked to write the bond enthalpy for bromine, that is different. That is breaking all the bonds in 1 mole of that's breaking all the bonds in 1 mole of covalent molecules. So that would be bromine to 2Br gas. All right, so you would hopefully know that the difference between, or the relationship between bond enthalpy, which is what we have here, and enthalpy of atomization is that this enthalpy of atomization is half the bond enthalpy. Okay, so I'll just clear that. Alright, and then finally we are looking to get the lattice enthalpy, the equation for the lattice enthalpy for calcium bromide. Now it doesn't say if it's dissociation or association. Okay, in CCEA, our exam board, we go for the dissociation all the time, just the lattice enthalpy. Dissociation, okay, so that would be starting with calcium bromide, the solid, going to the gaseous ions. Okay, so we have 2 bromide ions. Okay, that's our answer. Just tidy these other little bits up around it. Okay, show you the clear answer. So that's the enthalpy, the lattice enthalpy. Okay, and that's for dissociation, right? So we've got to draw our Born-Haber cycle. So again, we'll draw our Born-Haber cycle for calcium bromide, or sorry, for potassium iodide. Sorry. Okay, so this is a pretty easy one. Calcium, potassium iodide. I'll tell you what, I'm going to actually skip the potassium iodide one, and I'm going to go down to the strontium chloride because it offers a slightly different challenge. Potassium iodide is exactly the same as sodium chloride one, which is done earlier, except instead of sodium you've got potassium, instead of iodine you've got chlorine from earlier, right? So in this one, we draw the Born-Haber cycle, okay, for strontium chloride, and then use it to work out the enthalpy of What is it for the enthalpy? Yeah, so we're looking to work out the enthalpy of formation in this instance. Okay, so let's have a look then. Okay, just want to give myself a bit more room here. Okay, so again, like I always do whenever I'm drawing these guys, I start sort of down the bottom left hand corner and I start with the enthalpy of formation. So I've got strontium chloride, so it's starting off with strontium, which is a metal, so it's solid in this instance. And there's two chlorines, so chlorine is a gas at room temperature, so it's Cl2, I don't need to divide that by 2. Okay, and from there then I'm going to go to the enthalpy of formation, which is when I make 1 mole of the solid compound from its elements in their standard states, and I just label that. That's what we're trying to find, so there'll be no value for it in the table above. Right, okay. Then we go through our stages. Okay, so what we'll do first is we've got the solid strontium, but we can't ionize it until we've atomized it. So we're going to go strontium gas plus again Cl2. It's gas, it just stays as is. We'll just label that. That's delta H atomization. I'll not label it atomization of strontium. It's blatantly obvious that that is the case. I might do that in an exam, but I'm not going to do it here. Okay, strontium then. Gas has got to be ionized, so that goes to a +1. Remember, it's lost an electron, and you have to account for that electron. Okay, can't. Okay, that is first ionization energy of strontium. Okay, we go from first ionization energy. Strontium, remember, is a group 2 metal, so it's going to go to Sr2+. Okay. Keep an eye on your state symbols, even now when I'm doing these. And again, I look back and I've left out a state symbol. That'll cost me a mark. Okay, I've got 2 electrons to account for because we've gone through 2 ionizations. Okay, and the next thing then what we've got to do is to atomize. I'll just label that also. Second ionization energy of strontium. Then we're going to atomize our chlorine, so let's just write this out again. Okay, atomizing my chlorine will give me 2 Cl, which are also a gas. Oh, excuse me, wobbly hand. Okay, right, so that's fine now. All I've got to do is I've got an electron affinity. Okay, for my now remember, electron affinity is exothermic, so the convention is that we go back down again, and that will bring me to Sr2 plus gas. It doesn't change, plus 2 Cl minus the 2 electrons. Remember, they've gone now. Those are the 2 electrons that are in that. Okay, I'll just label that. So that's first electron affinity of chlorine, but remember it's multiplied by 2 because I'm electron affinity 2 ions of chlorine. And then we have our lattice enthalpy. So if we just go up here, let me find my lattice enthalpy. Yeah, so lattice enthalpy is written in the endothermic way. So that arrow is going up the way from the solid product there. Okay, so we've got to use this now to work out our enthalpy of formation, right, which is this. So essentially we're looking at this arrow. So we're starting, we've got to find our Hess's law application. We've got to find in another way, another route. So we're starting here and we're going to our product, our same product, but we're going via that route. Okay, now let's go through our values in the table here and assign them and make sure we don't have to multiply anything by 2, divide anything by 2. Okay, so enthalpy atomization of strontium, well that's fine. It's 1 mole of strontium and that's fine, 164. Enthalpy atomization of chlorine, so remember atomization is the formation of 1 mole of gaseous atoms. If you look here, we are having to make 2 moles of gaseous atoms. Okay, so that's going to have to be times by 2. First ionization energy of strontium, that's fine. Second ionization energy of strontium, fine. First electron affinity of chlorine, well we've got to do that times 2 as we said here. Okay, and then we've got our 2, 1, 1, 2. Now what I would do, because the lattice enthalpy is going, if you like, against the grain here, okay, that means that everything that I have from there down to there, I add it, okay, and then I take that away from it. Okay, alternatively, you can flip the sign of the 2, 1, 1, 2 and add that as well. It's up to you, but that's a good way to do it that I've just shown you there now, is to go through it. You might want to maybe pause this video here, do the calculation. It's a pretty good idea actually if you do that the whole way through these. If you just pause it whenever I start the question, have a go at it, and then follow me through and see if I so minus 3, 6. Okay, so if I've done everything right on my calculator, and that looks about right, I've done everything right on my calculator, and that's not always the case. Okay, I'm getting an answer for 826. Looks about right to me. Should be exothermic, and probably about that value of exothermic. So hopefully that's fine. Anyway, you can see the method, and I guess that's the most important part. Okay, so let's have a look at this one. This is magnesium fluoride, and we've got to, from this here, we've got to calculate our enthalpy of lattice. Okay, so first thing we've got to do is fill in the table. Exactly same. Should be getting really pretty good at these now, guys. So we've got magnesium solid, starting off same place as we always do, plus our F2 gas goes to with our enthalpy of formation, MgF2. Remember, that's now solid. It's enthalpy of formation. So we've atomized it here. Okay, we've got second electron affinity has happened up here. We've got an Mg2 plus. So this must be our first electron affinity happening here. Remember to count. Remember your state symbols. Okay, really easy to drop marks, guys. Remember, one electron. Nothing's happening to the fluorine yet at all. So just leave it. Okay. Here to here, then we have atomized fluorine. Let's see what they give us over here. Atomization, yeah, atomization of fluorine, that's fine. Alright, so that's 2 times the atomization. Okay. And then down here we have our electron affinity of the fluorine, and again with that'll be times 2. So that's Mg2 plus gas plus our 2F with electron Fe there, and again don't forget your gas, and we're looking to calculate out our lattice enthalpy this time. So this is our lattice enthalpy here, that's our gap. Okay, so if we just remind ourselves that the enthalpy of formation is equal to the sum of all the other delta H's minus, because it's going in the dissociation direction, minus the lattice enthalpy. So our enthalpy of formation there we've got at minus 1123 is equal to first electron affinity of fluorine. Okay, so that's minus 348. Remember, multiply that by 2. Okay, next one down is the atomization of fluorine, which is 79. Remember, atomization is only 1 mole of gaseous atoms being produced. First electron affinity of magnesium, 736. It's just fine on its own. Second ionization energy of magnesium is 1450, and then the atomization of magnesium is 150. Okay, and it does just 1 mole of magnesium getting atomized. I don't need to do anything to that. 50. Okay, plus 736. Plus 279s minus 2 times 48. Oh, syntax error, never good. Okay, so this all gives me, according to my calculations, 1798. So therefore, enthalpy of formation, which was minus 1123, equals 1798 minus the lattice enthalpy. Okay, so take that plus the 1, 1, 2, 3 gives me 2, 9, 2, 1. Okay, is my lattice enthalpy. That's a positive value. Remember, it's endothermic. It's the enthalpy of dissociation. Put the units on it. It's kilojoules, moles to the -1. Okay, a bit messy, but hopefully you can see the principle behind it. Okay. Right. So let's just clear that away, and we'll start the next one if it's worth doing. The next one we're being asked to work out something slightly different. So we're being asked to get the electron affinity. We haven't been asked to do that. Generally these questions are work around the lattice enthalpy, but on occasion we'll be asked to get the electron affinity, and that's fine. We'll do that. Just skip it down a page to give us a bit more room. Okay, so right, I'm going to try this time, guys, without actually drawing out the Hess's law cycle, because that's a really time-consuming thing to do in an examination. So you really, if you got a question like this, it doesn't ask you to write the lattice enthalpy, it doesn't ask you to write the Born-Haber cycle. So it's better that you don't have to sit and do that in an exam situation, because as I say, it is really very time-consuming. Right, so we've got to get the electron affinity of chlorine here, and again, it's exactly the same again. I've got to try now and envisage all of these enthalpy changes that are going on. So the enthalpy formation is -436. So just remember, I suppose it might be useful if you wrote it's for potassium chloride. So the good thing is we have 1 potassium and 1 chlorine in here. So okay, you've got to bear that in mind. Okay, so the first ionization of potassium is 420, and that's fine. I've only got 1 potassium. Okay, the bond dissociation energy of chlorine is 244. Now we need to be careful there, because bond dissociation, remember, is breaking all the bonds in 1 mole of covalent molecules, which would give us 2 chlorines. So this has got to be plus 244 over 2 this time. It's only half that energy. Okay, we've got plus or minus 706. We'll just do minus 706 there. Okay, for that's sorted. First ionization energy sorted. Standard, we missed out the standard enthalpy atomization of potassium. That's 90. Put that in. And the standard enthalpy for the formation of potassium chloride is on the other side. So we've got to get the electron affinity this time. Okay, so let's tot up what we've got on the right hand side there. Plus okay, so I have minus 436 equals minus 74 plus the electron affinity. Okay, hopefully that makes sense. So so that brings my electron affinity down then at minus 360. Okay, so that's what I'm getting as the electron affinity of chlorine here. I can probably pop up here somewhere and find the electron affinity of chlorine. Yeah, so in this table here was given as minus 364. So yeah, hopefully I'm bang on there. Okay, well just put the units in for that, guys. Just keep yourself right, always with units. You drop marks, okay? Calculate the lattice enthalpy for sodium chloride in that one. I think we've already done that, or very similar. The electron affinity for chlorine. I'll do this one actually because it is very similar to the one above, but it's a little bit different. There's something in it that can catch you out, and we'll just I'll just make you aware of it. All right. So again, just remind ourselves. Okay, I know we've probably know this. It's the sum of all the other delta H's minus the lattice enthalpy. Okay, so what they've done this time, instead of saying that something is the delta enthalpy of formation, they've actually given you the equations, and you've got to deduce what's what. So enthalpy of formation is the bottom one here. The elements turning into 1 mole of the solid, so it's 795. the sum of all the others. So just remind yourself that calcium is CaCl2. So we've got here, first of all, atomization energy of calcium, so that's 190. We only need 1 mole of calcium, so we leave it at 190. We've got first and second electron affinities of calcium put in together here. Okay, so don't be looking for the first and the second. That's what we've had in lots of the previous examples, but here they've coupled them together. All right, we've got, this is the atomization energy of chlorine. Okay, but plus 121. But look, we've got 2 chlorines required here, so we need the atomization energy of chlorine times 2. Okay. All right. So I'll just tick these off as I go along because it's good to know what you've covered. Okay, then we've got here, this is the lattice enthalpy, the gaseous ions joining together. All right, so that is plus, you can do minus 2184. Okay, so because remember it's minus the lattice enthalpy up here, so that just becomes plus 2184. All right, and then it's all of that plus the electron affinity of chlorine. Now, this is where we need to be careful, because we're doing the electron affinity of chlorine. We have 2 Cl gas at this stage for the electron affinity, plus the 2 electrons lost from the calcium to go to 2 Cl minus for the electron affinity. So in actual fact, this value, the number that we get here would be the electron affinity twice. So what we'll have to do to get our final answer, basically, is what I'm saying, is we'll have to divide that by 2, and that was a little trip in this. The gap, the missing value between the left hand side of the equation and the right hand side of the equation wasn't the electron affinity, it was actually the electron affinity times 2. Okay, right, so I'm just going to top this up here. Okay, so that gives me on the right hand side 795 equals 4346. Okay, that seems exceptionally high. So see, I've clearly done something wrong here on a calculator somewhere along the lines. Minus calcium, let me add that up here. 0. Hold on. This is, yeah, I've got a cut out here, haven't I? Right. So normally we write our enthalpy for the lattice enthalpy for the dissociation. This one has rather sneakily been given to me, and I fell into the trap. The lattice enthalpy has been given to me as the association. Okay, so a bit of a lesson there, guys. I got a massive figure of 4,346. That would have made the electron affinity of chlorine extremely high. Okay, so if you do get a really odd looking number, go back, double check. Right, so we've got calcium, the lattice enthalpy here giving us the association. So actually, that is that. Okay, that should be minus. Okay, right. So, yep, probably a good lesson there for you guys to pick up in my humiliation. Okay, so that gives me, that's more like it. So let's get rid of that. Gives me minus 22 plus 2 times the activation energy for that. So let's go to 5 equals that. 2 gives me that. Okay, so the energy gap that I'm missing here at the minute comes out at 773 minus 773. But remember, I've got to divide that down by 2, and that gives me an energy value for the electron affinity of 386.5 kilojoules per mole. Now that's different. We've had 3 energy of electron affinity for chlorine here, and they've all been different. And that's what examiners do. They make the answers for these very common questions a little bit different just by tweaking the numbers a little bit. So, for example, if you did do this question before you went into the exam, got the electron affinity of chlorine to be minus 386.5, and then that question came up in the exam, don't automatically think it will be minus 386.5, okay, because it probably won't be. They'll fiddle about with the figures a little bit just to make it prevent people who've revised so are just memorizing that and actually being able to just regurgitate that value. All right, so just be cautious of that. Okay, guys, I'm going to leave it there. That's loads. I think I've probably covered pretty much every base that I can cover to allow you to have a good go at the lattice enthalpy and the Born-Haber cycle questions. Okay, so you've got this booklet of questions here with you. You've got a textbook with questions in it, so you've got all the answers to all of those. So I would suggest that you work away and make sure that you are on point with regard to your Born-Haber and your lattice enthalpy calculations.